Welcome to this tutorial on enterprise AI system design. In the world of artificial intelligence, there is a world of difference between a clever prototype built in a lab and a robust mission-critical system deployed within a large organization. That is the difference, what we call enterprise AI. So what exactly is it? At its core, enterprise AI refers to the strategic application of artificial intelligence to enhance, automate, or transform business operations within large organizations. This isn't about building a model for Kaggle competition. It's about engineering a business capability that must be reliable, scalable, secure, and governed. Failure isn't just a lower score on a leaderboard. It can mean significant financial loss, reputational damage, or legal consequence. Because of these high stakes, any enterprise level AI project must satisfy three critical, non-negotiable requirements. Number one, consistent performance at scale. The system must deliver reliable and accurate results under the pressure of real-world workloads, which can involve millions of users or petabytes of data. Number two, legal and ethical integrity. The system must adhere to all relevant laws, regulations, and ethical standards for its specific use case. This includes everything from data privacy laws to the principle of fairness. And number three, the system decision-making process must be transparent enough to build and maintain user trust. Stakeholders from internal users to external regulators need to understand and have confidence in how the AI arrives at its conclusion. These three pillars, performance, integrity, and transparency, form what can be called the enterprise AI triad of constraints. They are not independent goals to be checked off from a list. They are tightly coupled set of forces that are often in tension with one another. The art of enterprise AI system design is the art of balancing these constraints. Consider this. A highly complex deep learning model might achieve state-of-the-art performance on a given task. However, its very complexity can make it a black box, failing the transparency requirement. The lack of explainability isn't just a technical issue. It can create serious legal problems, for example, by violating a consumer's right to explanation for an automated decision under regulations like GDPR. Conversely, a simple, easily interpretable model like linear regression is highly transparent, but may lack the predictive power to perform adequate at an enterprise scale. Throughout this video, we'll explore how to navigate these trade-offs. We'll move beyond the model itself to examine the entire ecosystem required to support it. This includes the architecture, the operational success, the security frameworks, and the governance structure. This holistic view is essential because AI is not just technology, it's a socio-technology. It carries profound ethical risks concerning bias, data ownership, privacy, and cybersecurity, which must be managed alongside traditional technical and operational risks. This tutorial will give you a comprehensive blueprint for designing, building, and maintaining AI systems that are not just intelligent, but are also robust, responsible, and ready for the enterprise. With our foundational philosophies established, we can now turn to the core architectural principles that bring them to life. An enterprise AI system must be engineered to handle the immense demands of the modern data and computation while remaining stable, responsive, and reliable. This section covers the critical concepts of scalability, robustness, availability, and performance. Scalability is the ability of a system to handle a growing amount of work by adding resources. In the context of AI, this isn't just about handling more user traffic. It's about handling larger datasets, more complex models, and greater computational demands. There are two primary ways to create a scale system: vertically and horizontally. Vertical scaling, this involves increasing the resources of a single machine, for example, adding more powerful CPUs, more GPUs or RAM, It is generally simpler to implement because it doesn't require change to the application's logic. The same code runs on a more powerful server. Vertical scaling has a hard physical limit. You can only add so much power to one machine and it creates a single point of failure. If one of the powerful server goes down, the entire system fails. The other one is horizontal scaling. This involves adding more machine to a system and distributing the workload across them. This is the foundation of modern cloud-native distributed system. It offers nearly limitless scalability and high availability, as the failure of one machine does not bring down the entire system. However, it introduces significant complexity in terms of network communication, data consistency, and load balancing. For AI systems, the choice between these patterns is not uniform across the entire application. A crucial architecture insight is that scaling dichotomy between model training and model inference. These two phases of AI lifecycle have fundamentally different, often opposing scaling requirements, which demand distinct architectural solutions. The first case, which is model training, it requires a massive, long-running, batch-oriented process. The goal is to process a huge dataset to produce a trained model as quickly as possible. This is a throughput optimized problem. For LLMs, training on a single machine is impossible. Therefore, training is almost always scaled horizontally using distributed techniques. The two main patterns are data parallelism, number one, and model parallelism. In case of data parallelism, the dataset is split into smaller chunks and a complete copy of the model is placed on each worker. For example, a GPU. Each worker trains on its subset of data and the resulting model updates. Gradients are synchronized and aggregated across all workers to produce the final model. This is the most common approach when the model can fit on a single GPU, but the dataset is massive. And in terms of model parallelism, the model itself is too large to fit into a single GPU's memory. In this case, the model is split with different layers or paths placed on different workers. The data is then passed sequentially through these workers to complete the training step. This is more complex to implement but is necessary for training today's largest foundational model. Model inference, in contrast, is typically a series of short, real-time, stateless requests. When a user sends a query to an AI application, they expect a fast response. This is a latency-optimized problem. The architectural pattern for handling a high volume of independent real-time requests is to run multiple stateless copies of the inference application behind a load balancer, scaling horizontally as traffic increases. This dichotomy leads to a bifurcated architecture, a high-cost, high-throughput, horizontally scaled training environment optimized for batch processing, and a cost-optimized, low-latency, horizontally scaled inference environment optimized for real-time requests. A mature MLOps platform is the bridge that manages the model's journey from the training cluster to the server cluster. Ignoring this distinction leads to gross inefficiencies such as using expensive, powerful training hardware for simple inference tasks or trying to sever real-time requests with batch-optimized architecture. An accurate model that is brittle and fails unpredictably in real world is not just useless, it's dangerous. Robustness is a measure of an AI's model's capability or ability to maintain its performance and reliability when faced with uncertainties of the real world, such as noisy data, unexpected inputs, or even malicious attacks. It's a measure of resilience, not just a benchmark accuracy. In an enterprise setting, robustness is paramount because it directly impacts user trust, operational stability, and financial viability for the AI system. A robust model is less sensitive to outliers in the data, requires less frequent retraining, and is essential for mission-critical applications like autonomous vehicles, medical diagnostic, and financial fraud detection. Building robust AI system requires focusing on three main components. The first one is data diversity. The foundation of robustness is the data used for training. A model trained only on clean, perfectly curated data will be fragile when it encounters the messiness of the real world. A robust model must be trained on the rich, diverse data set that encompasses a wide range of scenarios, conditions, demographics, and potential noise. The second one is model generalization. This is the model's ability to apply what it has learned to a new, previously unseen data, rather than simply memorizing the training set. A model that generalizes well understands the underlying pattern and principles in the data, allowing it to perform reliably across different contexts. Poor generalization leads to overfitting, where the model is highly accurate on training data, but it fails on new data. The third one is adversarial resilience. This is the model's ability to withstand deliberate, malicious attack and attempts to deceive it. Adversarial attacks involving making small, often imperceptible perturbations to an input that are designed to cause the model to make a catastrophic error. For example, adding a tiny, specially crafted patch to a stop sign could make a self-driving car's perception system misclassify it as the speed limit sign. Building resilience techniques like adversarial training, where the model is explicitly trained on these kind of deceptive examples to learn how to resist them. A critical pattern for maintaining robustness over time is the data flywheel. This is a continuous feedback loop where the system is designed to learn from its own operations. Data flows into the system, is processed, and then fed into the AI models. The output of these models are then continuously monitored for the performance. Any degradation, drift, or failure is flagged, and the new data representing the model's real-world experience is fed back into the training pipeline to create a new, improved version of the model. It's important to understand that the pursuit of robustness can sometimes be at odds with the pursuit of maximum accuracy on a static benchmark. A model's accuracy is typically measured against a clean, known validation dataset. Robustness, however, is about performance on unknown, future, and potentially dirty data distributions. Techniques that enhance robustness, such as adding noise to the training data or performing adversarial training intentionally, making the learning task harder. This might slightly lower the model's peak accuracy on the pristine validation set, but makes it far more resilient and reliable when deployed in real world. For any critical enterprise system, this is a necessary and deliberate architectural trade-off. A model that is 97% accurate but performs reliably across all expected conditions is far more valuable than a model that is 99% accurate on lab data but fails unpredictably in production. When we build distributed systems, which nearly all scalable AI systems are, we are bound by a fundamental law of computer science known as the CAP theorem. First, introduced by Eric Brewer, the theorem states that any distributed data store can simultaneously provide two of the following three guarantees. The C stands for consistency, which means that every read request receives the most recent write or an error. All nodes in the system see the same data at the same time. And A stands for availability, which essentially means every request receives a non-error response without the guarantee that it contains the most recent write. The system is always responsive, even if it means returning potentially stale or wrong data. The P stands for partition tolerance. The system continues to operate despite an arbitrary number of messages being dropped or delayed by the network between the nodes. This is what we call in any real-world distributed system, network failures are inevitable. A server can crash or a network link can go down. Therefore, partition tolerance P is not optional. It must be supported. This means that during a network partition, an architecture must make a difficult choice between the remaining two guarantees, consistency or availability. This choice has profound implication for databases and data stores that underpin an AI system. The decision between a CP, that is the consistency plus partition tolerance system, or an AP, availability plus partition tolerance system, is not merely a technical one. It is a direct reflection of the business's tolerance towards different types of risk that is willing to undertake. And the CP system, which prioritizes consistency. When a partition occurs, a CP system will choose to preserve data consistency. If it cannot guarantee that a read will return the most up-to-date information, it will return an error or timeout, thus sacrificing availability. This is the right choice for applications where incorrect or stale data carries a very high business risk. The AI use case example would be a real-time fraud detection system. If the model makes a prediction based on stale transaction data, it could either approve a fraudulent transaction or decline a legitimate one, both with significant financial consequences. In this case, it is a far better choice to be serving a temporarily unavailable than make a decision based on wrong information. An example could be MongoDB, Redis, or HBase are often configured as the CP systems. And moving over to the AP systems, which prioritizes availability, especially when a partition occurs, an AP system will choose to remain available. It will respond with the best version of data it has access to, even if it's out of date. This is the right choice for application where system downtime is more costly than a potential for a slight data staleness. The AI use case example could be a personalized content recommendation engine on a streaming platform. If the system doesn't have the user's most recent viewing history, example, if it's unaware of a movie that they have finished 10 seconds ago, the recommendations might be slightly less optimal. This is a minor inconvenience. However, if the recommendation service is unavailable and the user sees a blank screen, they are likely to get frustrated and leave the platform. Here, the business risk of unavailability is much higher. Example of such databases include Apache Cassandra, Amazon DynamoDB, CouchDB are like the classic examples of AP system. The modern view of the CAP theorem or CAP theorem acknowledges that this isn't always a rigid binary choice. Many modern databases offer turnable consistency, allowing developers to choose between the level of consistency required for different operations. Furthermore, AI can be used to create systems with adaptive consistency, which can dynamically shift the balance between C and A based on the real-time state of the system, such as network condition or the request volume that the system receives. And I feel ultimately the CAP theorem focuses on a business level risk assessment at the very beginning of the design process. The architect, I think, must ask, what is the business cost of being wrong versus the cost of being down? The answer to that question will dictate the fundamental choices of data storage architecture for the AI system that we're about to build. Performance is a cornerstone of any enterprise system, but in AI, performance is a two-sided coin, latency and throughput. These two metrics are often in a trade-off relationship, and understanding how to balance them is critical for designing a successful system. Latency is the time it takes for a single request to be processed from start to finish. It's a measure of delay, or you could say responsiveness. For interactive AI applications, especially those that involve LLMs, Latency is often measured as time to first token, or TTFT, the time from when a user sends a prompt to when they see the first word of sequence in the response. Low latency is absolutely critical for applications that require real-time interactions, such as chatbots, online gaming, or virtual assistants, as delays can make the experience feel sluggish or unresponsive. And coming over to throughput, throughput is the amount of work or volume of data that a system can process in a given period. For AI system, this might be measured in queries per second (QPS), or for LLMs, tokens per second (TPS), across all concurrent users. High throughput is vital for systems that need to handle a large volume of requests or process massive amounts of data, that too in batches, such as a system for analyzing financial reports or a high-traffic e-commerce website. The fundamental trade-off between latency and throughput is best illustrated by the technique of request batching. Imagine an inference server receiving a bunch of requests. It can process them one by one as they arrive. This minimizes the latency for each individual request, and alternatively, it can wait a few milliseconds to collect a batch of requests and process them all together. This parallel processing can drastically increase and overall throughput, but it comes at the cost of increased latency for each and every individual request in that batch, as each had to wait to be grouped together. The decision of whether to optimize for low latency or high throughput is not purely technical one. It is a product design choice driven entirely by the expected user experience. The architecture must be tailored to the application's interaction model, so to speak. Then, in cases where the latency is super sensitive, for example, a conversational AI, in the case where a user asks a question and waits for a response in real time, any delay makes the interaction feel super unnatural and irritates the user. Here, minimizing latency is the primary goal. The architecture should prioritize processing requests individually or in very small batches, and techniques like streaming, where tokens are sent back to the users as they're generated rather than waiting for a full response, is used to improve perceived latency. Other strategies include using in-memory caching, content delivery networks or CDNs to reduce network distance, optimizing model size, and using faster communication protocol. For throughput sensitive applications, like for an AI system that performs offline analysis of daily sales data to generate a forecast, no user is waiting in real time. The goal is to process a massive amount of data as efficiently and cost effectively as possible. Here, maximizing throughput is a priority. The architecture should be designed around large-scale batch processing, grouping thousands of data points together to maximize hardware utilizations. And other strategies include horizontal scaling, parallel processing, and asynchronous workflows. Therefore, the first question an architect must ask is, what is the user's expectation of responsiveness for this specific task? The answer determines whether on the latency throughput spectrum the system needs to operate and dictate the appropriate architectural pattern and optimization techniques. Building an enterprise AI system is not a one-off project. It's a continuous cyclical process. Machine learning operation, or MLOps, is the discipline that applies DevOps principle to the machine learning lifecycle. It aims to unify model development, the ML part, with the model operations, the ops part, to standardize and streamline the continuous delivery of high-performing models in production. This section provides a detailed breakdown of the key stages in a mature MLOps lifecycle. The adage, garbage in, garbage out, is amplified in AI systems. The foundation of any robust and reliable model is a well-architected data pipeline and a systematic approach to managing the features that feed the model. Enterprise AI systems require automated, scalable, and reliable data pipelines to handle the ingestion, pre-processing, and transformation of data. These pipelines are the arteries of the AI system, and they must be designed with production realities in mind. Pipelines must be able to process batch data, for example, historical records from data warehouse, streaming data like real-time user clicks or from an application, structured data, and also unstructured data. Building those pipelines require technologies designed for scale and resilience. Tools like Kafka are excellent for high throughput, real-time event streaming and act as a central, durable log for all data events. Streaming processes framework like Apache Flink or Apache Spark Streaming can then consume from Kafka to perform real-time transformation and aggregation. One of the most critical challenges in production ML is training serving skew. This occurs when the feature used to train the model are calculated differently from the features used for inference in production, leading to a silent degradation of model performance. A feature store is a centralized repository designed to solve this problem. It provides a single source of truth for features, storing both the feature definitions and the materialized feature values. It ensures that the exact same feature logic is used during both training and inference, eliminating the skew. It also serves feature with low latency for online inference and provides historical feature data for training, bridging the gap between the batch and real-time world. The core tenet of MLOps is reproducibility, the ability to recreate a model and its results perfectly. This is essential for debugging, auditing, and reliable iteration. While traditional software engineering focuses on versioning code, ML systems are more complex. True reproducibility rests on what can be called the golden triangle, versioning three distinct but interconnected artifacts. First is the code, which are the algorithms for data processing, feature engineering, and model training, must be versioned, typically using Git. And the same code run on different data will produce a different model. Therefore, the specific version of the dataset used for training must be tracked and versioned. Tools like DVC, data version control, are designed for this purpose. And the last one, model. The trained model itself, a collection of weights and parameters, is an artifact that must be versioned and stored in a model registry. Tools like MLflow provide this capability, allowing you to track model versions, their associated metrics, and their lifestyle stages, for example, like staging, production, or archive. A failure to version any of these three artifacts breaks the chain of MLOps, making the system opaque and unmanageable. A mature MLOps platform is fundamentally a versioning and artifact management system built around this triangle, with the feature storing act as a key enabler that connects version code and data to produce consistent version features for the model. In MLOps, the principles of continuous integration and continuous delivery / deployment or CI/CD are adapted to automate the entire machine learning lifecycle. However, CI/CD for ML is significantly more complex than for traditional software development because it must treat data and models as first-class citizens alongside the code. A CI/CD pipeline for ML is the central nervous system of the entire MLOps platform. It's not just a deployment script, it is the operational embodiment of organization's AI strategy. orchestrating every step from data ingestion to model monitoring in a fully automated loop. Speaking about the key characteristic of an ML CI/CD pipeline, the first one that sticks out is the automated triggers, and that is the key difference from the traditional CI/CD, is that an ML pipeline can be triggered not only by a code change, for example, a new feature engineering script, but also by the detection of new training data or by a monitoring alert signaling model performance degradation. The next characteristic would be continuous training. The integration phase in MLOps is often referred to as continuous training. When triggered, the pipeline automatically ingests the latest data and code, retrains the model, and evaluates it. And it also has comprehensive and automated testing as well. The testing in an ML pipeline goes from beyond the typical unit and integration test. It also includes data validation, in which automatically checking new data for schema integrity mainly, also for statistical properties of the data and the drift compared to the training set. Also automatically evaluating the newly trained model's performance on a holdout test set, which includes checking not just for accuracy, but also for fairness, bias, and ensuring its performance is better than the currently deployed model. Also comparing the new model to the older versions of the quantified performance improvements and understanding the decay rates. And moving over to continuous delivery or deployment, the CD of the CI/CD, that is, if all tests pass, the pipeline automatically packages the model, maybe in a Docker container, and its dependencies, it kind of versions it and registers it in the model registry. The continuous deployment stage then automatically deploys this new model to production environments. To de-risk this process, deployments are often done using advanced strategies like coronary release, in which the new model is rolled out to a small subset of users first. Its performance is monitored closely before a full rollout. You have something called the shadow mode, in which the new model runs parallel with the old one, receiving the same production traffic, but without its predictions being served to users. This allows for performance comparison in real-world setting without the risk. And then you have finally the A/B testing, wherein different models are served to different user segments to empirically measure their impact on business KPIs. This automated end-to-end pipeline transforms the ML ops lifecycle into a dynamic, adaptive system that can learn and correct itself, which is the ultimate goal of ML ops. Once a model is trained and validated, it needs to be deployed into a production environment where it can serve predictions. This requires a robust, scalable, and manageable serving architecture. A best practice for a complex AI application is to adopt a microservice architecture instead of building a single monolithic application. The system is broken down into a collection of small, independent services, each responsible for a specific business capability. For an AI application, this might look like a user management service for handling accounts and authentication, a data ingestion service for collecting real-time events, a feature engineering service for transforming raw data into features, an inference service that hosts the ML models and exposes a prediction endpoint, a post-processing service that might take the model's raw output and format it for the user. This approach offers immense benefits. Each service can be deployed, developed, and scaled independently using best technologies for its specific job. For example, Netflix famously uses hundreds of microservices to power its platform, with dedicated services for recommendation, user profile, and content metadata. As the number of microservices and AI models grow, managing traffic, security, and policies becomes super complex. An API gateway is a specialized API gateway that acts as a single centralized point for all AI-related requests, while a traditional API gateway handles routing, authentication, and rate limiting. An AI gateway adds capabilities specifically tailored for the AI workload. The AI gateway is evolving into the primary policy enforcement endpoint for governance, security, and cost control in enterprise. By intercepting every AI request, it provides a critical choke point to apply rules and monitor usage before requests each expensive internal models or third-party APIs. Some of the key features include tracking metrics like token usage and cost per request, which are crucial for LLMs, then performing prompt validation, transformation, or even redacting personal identifiable information or PII before sending a prompt to a model, which is critical security control. Then you have to manage API keys for various third-party AI services like OpenAI, Anthropic, or Gemini in a single place rather than scattering them across different. Then intelligently routing requests to the most appropriate model or server based on the request content or real-time server metrics. Load balancing distributes incoming traffic across multiple server instances to ensure high availability and prevent any single server from being overwhelmed. Most inferences services are stateless, meaning each request is independent and can be handled by any server. This makes them easy to scale horizontally with simple load balancing algorithms like route robin or least connections. However, many AI applications, particularly multi-turn conversational AI, are stateful. They need to maintain the context of a conversation over multiple requests. For these applications, the load balancer must implement session persistence or sticky sessions to ensure that all requests from a single user's sessions are consistently routed to the same server that holds the conversational state. This is often achieved using cookie-based or IP affinity. Advanced use cases like serving LLMs with prefix caching. Simple session persistent is insufficient. A more sophisticated approach is model-aware routing, where the load balancer makes a decision based on real-time metrics from the model servers themselves, such as queue length, GPU utilization, or KV cache usage. A powerful technique for this is CHWBL, consistent hashing with bounded loads. This algorithm hashes the content of a request, for example, the conversation prefix, to route it to a specific server, maximizing the chance of a cache hit. Crucially, it also considers the current load on the servers, preventing any single server from becoming a hotspot, thus balancing cache affinity with load distribution. Making a model predict is easy. Making it predict quickly, cheaply, and at scale is a significant challenge. Inference optimization is a critical step to ensure that a deployed AI system is both performant and cost-effective. These techniques aim to reduce the size and computational complexity of a model, which directly translates to lower latency, lower memory requirements, and reduced infrastructure cost. The first one is quantization. This is the process of reducing the numerical precision of the model's weight and activation. For example, converting 32-bit floating point number, the FP32, to an 8-bit integer, INT8. This can significantly reduce the model's memory footprint and speed up computation on hardware that supports lower precision arithmetic, often with minimal impact on accuracy. Pruning is a technique that involves identifying and removing redundant or unimportant parameters like weight or connections from a neural network. This creates a sparse model that is smaller and computationally cheaper to run. Next is knowledge distillation. In this approach, a large, complex teacher model is used to train a smaller, more efficient student model. The student model learns to mimic the outputs of the teacher model effectively, transferring knowledge into a more compact form that is cheaper to deploy. And in terms of intelligent caching strategies, they involve storing frequently accessed data or computation results in a faster in-memory data to avoid repeating slow operations like database queries or expensive model inferences. The choice of caching strategy involves a crucial trade-off between latency, cost, and data consistency. An aggressive caching can dramatically reduce latency and cost, but increases the risk of serving stale data. There are two most popular in-memory caching systems. The Memcached is a simpler, multi-threaded, and highly effective for basic key-value caching. It's an excellent choice for high-throughput caching of simple, read-heavy data like raw API response. Redis is more of a versatile Swiss Army knife, and it supports a rich set of complex data structure like lists, sets, hashes, etc., offers data persistence, and has advanced feature like PubSub messaging and transaction support. This makes it more suitable for complex caching scenarios, such as caching user feature vectors in a hash, manageable real-time leaderboards with sorted sets, or acting as a message broker for ML workflows. And the last one is semantic caching. This is a cutting-edge caching strategy designed specifically for LLM application. Instead of relying on an exact match of the user's query, semantic caching uses vector embeddings to understand the meaning or intent of a query. If a new query is semantically similar to the previous one, the cached response can be returned. This dramatically increases the caching hit rate for a conversational AI, significantly reducing latency and the number of expensive calls to the LLM. Reddit, with its support for vector search, is also well suited to kind of implement semantic caching. Deploying a model is not the end of the MLOps lifecycle. It's merely the beginning of its operational life. Continuous monitoring is the process of tracking a model's performance in production to ensure it remains effective, fair, and reliable as real-world conditions change. Without monitoring, even best models will inevitably degrade over time, a phenomena known as model decay. Monitoring is the active sensory system for the entire MLOps platform. The signal it generates, such as drift detections, are critical inputs that trigger the automated self-correcting loop of a CI/CD pipeline. A comprehensive monitoring strategy tracks several categories of metrics. They could be operational metrics, which are standard software performance indicators like latency, how fast the predictions are being made, throughput, how many requests can it handle, system uptime, and error rates. And the second category is what we call the model performance metrics. These are data science metrics that measure the quality of the model's prediction, such as accuracy, precisions, recall, and F1 score. This requires access to the ground truth, the actual correct labels, which may be delayed in some applications. And you have model drift, which is the most critical concept in ML monitoring and refers to the degradation of a model's performance due to changes in data environment. And there are several types of drift. The first one is data drift, which is the statistical properties of the input data change over time. The model starts seeing data that is different from what it was trained on. For example, a retail demand forecasting model trained on pre-pandemic shopping behavior will likely perform poorly on post-pandemic data due to its shift in consumer habits. The next one could be a concept drift. The fundamental relationship between the input features and target variables change. The concept of the model learned is no longer valid. For example, in a fraud detection system, fraudsters may develop a new technique, meaning the pattern that once signaled fraud are now different. And finally, we have prediction drift, which the statistical distribution of the model's own predictions change over time. This is often powerful early signal for a data or concept drift, especially in cases where ground truth labels are not immediately available. And moving over to kind of strategies for mitigating these drift. So to kind of understand when a drift is detected, it triggers a response. This is not manual process in a mature MLOps system. It starts off with the analysis phase, wherein the first step is to understand the source of the drift. Is it a genuine change in the world, or is it a bug in the data pipeline? Example, a sensor is broken or a feature is now missing. Then you kind of move into the automated retraining to see if the drift is genuine. The most common response is to retrain the model on a new, more relevant dataset. The monitoring system can be configured to automatically trigger the CI/CD pipeline where a drift threshold is breached. The pipeline then ingests the new data, retrains, validates, and deploys the updated model, closing the MLOps loop. And then finally you have process intervention, and in some cases, immediate retraining might not be feasible. For example, when in cases where you don't have new label data, in these situations, the system might take other actions such as temporarily halting the model, adjusting its decision threshold to be more conservative, or flagging more cases for human review. This feedback loop, where production monitoring directly triggers automated retraining and redeployment, transforms the MLOps pipeline from a linear script into a dynamic self-healing system that continuously adapts to its environment. This is the core promise and power of the mature MLOps implementation. AI system, to be truly enterprise ready, it must operate with a robust framework of security, governance, and financial accountability. These are not optional add-ons. They are foundational pillars that ensure the AI is used safely, responsibly, and sustainably. AI introduces novel and complex security challenges that go beyond traditional cybersecurity. While protecting infrastructure with firewalls and access control is still necessary, securing an AI system means protecting the data, the model, and the integrity of the decision-making process itself. A guiding principle for modern security is zero trust, which dictates never trust, always verify. Every user, device, and service interaction must be authenticated, authorized, and continuously monitored, with no implicit trust granted based on network location. The attack surface for AI is unique. Traditional cybersecurity often focuses on protecting the perimeter of a system. AI security represents a paradigm shift where the asset to be protected is not just the data, but the behavioral integrity of the model. Many AI-specific attacks don't breach the system in a conventional way. They exploit the model's own logic to cause unintended and harmful behavior. This means security must be built into the application logic itself, not just bolted on at the infrastructure level. And some of the key threats, vectors, and their mitigations include data poisoning, which is, in this case, the attack involves an adversary maliciously injecting corrupted or mislabeled data into the training set to manipulate the model's behavior. For example, an attacker could subtly alter images of stop sign to teach a self-driving car model to misclassify them. And the mitigation for that would be strict data curation and validation processes, matching data integrity through access controls and audits, and using anomaly detection to identify suspicious training data. The next one could be model inversion of theft. These attacks aim to steal the IP of the model or sensitive data it was trained on. Model theft involves cloning a proprietary model, often repeatedly querying its API and training a new model on the input-output pairs. And model inversion is more insidious. It involves analyzing a model's output to reconstruct the sensitive private data used in its training. And the mitigation strategy could be implementing strong access controls on model's API, using techniques like differential privacy to add noise to the outputs, and monitoring for unusual query patterns that might signal a theft attempt. And you have adversarial attacks and prompt injections. This is a broad class of attacks when an adversarial crafts special inputs designed to deceive a deployed model. You have evasion attacks where small, often human imperceptible changes are made to an input to cause a misclassification. Like the example could be the stop sign patch that we previously discussed. And we have prompt injection, mainly valid for LLMs, where an attacker crafts a prompt that tricks the LLM into ignoring its original instructions and following the attacker's command instead. This can be used to bypass safety filters, reveal confidential information, or cause the model to perform harmful actions. And the mitigation for this is where the shift to behavioral security is more apparent by setting up input and output guardrails, sometimes called like the AI firewall, are essential. These are systems that inspect the content of prompt and responses. Input filter can detect and block malicious prompts, while output filter can check for hallucinations, toxicity, data leakage, or responses that violate privacy proactively. And red teaming is where a dedicated team tries to attack the system to find vulnerabilities, is also a critical practice. Then you have supply chain attacks where enterprises often use third-party models, open source libraries, and external APIs. Each of those components can introduce risk and vulnerabilities into the system. So the way to kind of mitigate them would be rigorous vetting of all third-party components, continuous vulnerability scanning of dependencies, and ensuring that vendors adhere to strict data security policies. Power requires control. AI governance is the comprehensive framework of rules, roles, processes, and standards that ensure an organization's AI system are developed and used responsibly, ethically, and in compliance with the law. It is the mechanism for operationalizing trust. A robust governance framework typically include a cross-functional governance board, which is an oversight body comprising of leaders from technology, legal, ethics, business, and compliance. This board is responsible for setting AI policies, reviewing high-risk use cases, and ensuring accountability across the organization. Next is a process to proactively identify and mitigate the technical, operational, and ethical risk associated with each AI deployment, which we call the risk management panel, or more like a framework, and also a commitment to ethical principles. Many organizations adopt a set of core principles to guide their AI development. A common set of principles can be remembered with an easy acronym called FEAT, where F stands for fairness, E stands for explainability, A for accountability, and finally T for trustworthiness. So in terms of fairness, we have proactively identifying and mitigating unintended biases. in data and models to ensure equitable outcomes for all user groups. And for explainability, making the model decisions transparent and understandable to build trust, enabling audits, and also to kind of comply with regulations. And moving over to the accountability bit of it is to kind of establish clear lines of ownership and responsibility for AI systems and their outcomes, including having clear incident response plans. So finally, in the trust bit of it is to kind of ensure the system is secure, it respects user privacy, and protects data ownership. A critical aspect of governance is navigating the complex and evolving landscape of regulatory compliance. Regulations like GDPR and HIPAA are just not legal checklists. They're fundamental, non-functional requirements that directly dictate AI system architecture. Compliance cannot be an afterthought. It must be designed into the system from inception. For example, GDPR's right to be forgotten poses a significant architectural challenge. If a user's data was used to train a large language model, which is a monolith model, it is technically almost impossible to remove their contribution without retaining the entire model from scratch. A prohibitively expensive task. This legal requirement forces architects to consider patterns like RAG, where personal data is never baked into the model, but it is retrieved from an external, deletable database at inference time. Similarly, HIPAAs. Minimum necessary standards require that an AI model only access the minimum amount of protected health information, that is PHI, needed for its task. This directly influences the design of data pipelines, often necessitating data anonymization or de-identification microservices to scrub data before it even reaches the model. This demonstrates why legal and compliance experts must be involved in the initial design of an AI system, as their requirements are as foundational as performance or scalability. AI, particularly large-scale deep learning, can be incredibly expensive. The compute resource for training, the cost of storing massive data sets, and per token pricing of powerful third-party LLMs can lead to spiraling, unpredictable cost. AI FinOps is the emerging discipline that brings financial accountability to AI workloads. It's a cultural and technical practice that aims to help teams make cost-aware decisions to maximize business value without stifling innovation. AI FinOps treats cost not just as an afterthought, but as a primary architectural metric, on par with latency and security. Every design decision is evaluated through the lens of its cost-performance trade-off. Discussing like some of the key cost drivers in enterprise AI, number one is training and inference are often GPU intensive, and GPU instances are super expensive. So the compute resources umbrella. The second is data storage and transfer, like storing petabytes of data and paying for data egress, transferring data out of cloud region can be a significant cost. The third umbrella is third-party API calls. Many Gen AI applications rely on external models from providers like OpenAI, Anthropic, or Gemini, which typically charge you per token that you have processed. And finally, you have the human/operational overhead, the cost of the actual teams that is required to build, monitor, and maintain these complex systems. And in terms of the key FinOps strategies, the first one is to be kind of aware of the cost infrastructure choices that you make from like on-prem versus like the cloud platforms. So cloud platforms like AWS, Azure, GCP offer flexibility, scalability, and a pay-as-you-go model, which is ideal for experimentations and workload with variable demand. It kind of eliminates the need for large upfront capital expenditure. And on the other hand, on-prem infrastructure provides maximum control and security and can be more cost-effective in the long run for highly predictable and stable workloads, but it requires a massive upfront investment and ongoing maintenance cost. For most organizations, a cloud or hybrid approach is preferred due to the rapidly evolving nature of AI technology itself. In terms of how to kind of purchase the compute, you use on-demand pricing for flexibility, but also leverage spot instances, the unused capacity at up to 90% discount for iterable workloads like model training. For predictable long-running workloads, secure committed use discounts or CUDs or reserved instances RIs to lock in savings of up to 40 to 60%. And in terms of the hardware and model efficiency, please do not use a massive expensive model. Then a smaller, more efficient one will do it. Analyze the trade-off between accuracy and inference cost. And in terms of model optimization, use techniques like quantization, pruning, and knowledge distillation to reduce computational requirements of your models. Also think about alternative hardwares, evaluate alternatives to expensive NVIDIA GPUs for specific workloads, custom application-specific integrated circuits like AWS or Google TPUs that can offer better performance per dollar. Thinking about data management layer, you can use tiered storage, moving less frequently accessed data to cheaper storage classes, like for example from hot to cold storage. Compress data using efficient formats like Parquet instead of CSV. Make sure to minimize cross-region data transfer to avoid high egress fees. And finally, the visibility and accountability bits of it, you can implement rigorous resource tagging to attribute cost to a specific project, team, or products. Use cloud cost management tools to monitor spending in real time and set up alerts for budget anomalies. And try to break down the total cost of ownership or TCO into its own parts, training, inference, storage, etc., to identify the biggest cost drivers and opportunities for optimization. This kind of cost-aware decision process allows an architect to answer critical questions like, is the 1% accuracy game using GPT-4 worth the 10x cost increase over a fine-tuned open source model? This is the essence of AI FinOps. Theory is essential, but its true value is realized in application. In this final part, we'll walk through a practical case study of designing a production-grade RAG system, summarize the common pitfalls that cause AI projects to fail, and conclude with a look at the future of enterprise. Let's start with one of the most powerful and practical architectural patterns for enterprise AI today: retrieval augmented generation, or simply put, RAG. RAG addresses the core limitation of large language models like knowledge cutoff and hallucination by grounding them in factual, up-to-date, and domain-specific information. Instead of trying to bake all knowledge into the model's parameter through expensive fine-tuning, RAG externalizes the knowledge into a verifiable data source. This decoupling of knowledge and reasoning makes the entire system more modular, manageable, and trustworthy. And here's how it works in practice. Everything starts with the offline indexing pipeline, which builds the system's knowledge base. First, in step 1, data sourcing, we begin by sourcing documents from various enterprise systems like Confluence or SharePoint or whatever source system that is specific to your company, cleaning them and standardizing their formats. Next, in step 2, which is called chunking, these documents are broken down into smaller, manageable chunks of text. This is a critical step. Chunks that are too small lack context, while chunks that are too large add noise. Then in step 3, each chunk is passed through an embedding model, which converts the text into a high-dimensional numerical vector that captures its semantic meaning. Finally, in step 4, these vector embedding, along with their original text and metadata, are stored in a specialized vector database. Next, we have the real-time inference pipeline, which responds to a user's query. It starts with step 1, wherein a user's query is passed through the same embedding model to create a query vector. Then, in step 2, the system performs a similarity search in the vector database to find the text chunks that are most semantically relevant to the query. Then, in step 3, the most relevant chunks are then combined with the original query to create an augmented prompt. And finally, in step 4, this augmented prompt is sent to the LLM, which now has both the question and the factual context needed to synthesize a final grounded response. A key production consideration is choosing the right vector database. The choice depends on factors like scalability and features. Key players like Pinecone, a fully managed service known for its ease of use, VV8, an open source option with a strong developer experience and hybrid search capabilities, and Melvis, a highly scalable open source solution designed for massive datasets. Despite the immense potential of AI, many enterprise projects fail. These failures are rarely due to the algorithm itself. They're almost always symptoms of a failure in systems thinking. Let's look at the most common pitfalls and how to avoid them. First, misaligned objectives. This is building technology for technology's sake, not solving a clear business problem. The solution is to always start with a measurable business KPI. Second, poor data quality. The classic garbage in, garbage out problem. The solution is to treat data engineering and governance as a first-class priority. Third, the POC trap. This is mistaking a lab prototype for a production-ready system. The solution is to build with production-scale security and monitoring in mind from day one. Fourth, lack of user adoption. A technically sound system that users don't trust or use. The solution is to engage end users throughout the process and invest in explainable AI. Finally, insufficient integration. Creating a standalone AI island disconnected from the core business system. The solution is to design for integration using microservices, architecture, and have lots of well-defined APIs. Where does this leave us? We have journeyed through complex landscape of enterprise AI system design. We've seen that building a successful system requires a synthesis of robust architecture, mature MLOps, and a deep commitment to security, governance, and cost management. The future of AI will be defined by organizations that can master this holistic approach. The landscape is constantly evolving towards more powerful, multimodal, and autonomous agentic AI systems. As this technology advances, the principles of robust system design will even become more critical to ensure they are reliable, secure, and aligned with human values. The fundamental challenge will remain the same: to build systems that are not just intelligent, but are also reliable, scalable, secure, and ultimately aligned with human values and business objectives. That is the true meaning of engineering for enterprise. Thank you for joining this comprehensive tutorial. We hope this provides you with the foundational knowledge and strategic framework to design and build the next generation of enterprise AI systems.